Welcome to Circuit Valley. I'm Gaurav. Today I'm going to make a next video in my multi-part video series. This video is going to be 11th video. In this multi-part series, we try to decode every single protocol or every single digital bus that is available in the embedded environment. Till now, we have tried to decode SPI, I2C, UART, RS232, CAN, LIN. We have also tried to decode flex ray. We have decoded parallel buses and wire-tapped Ethernet. So we have covered almost every protocol you can imagine. Now we are going to cover one really high-speed bus. We are going to talk about USB, and we will try to decode every type of USB you can imagine. We are going to start with USB LS, which is low speed 1.5 megabit per second. Then we will go to USB FS, which is 12 megabit per second. We'll go to USB HS10, which is 480 megabit per second. And in the end, we will try to also decode USB 3.0 with 5 gigabit per second. So decoding USB 3.0 is going to be very, very interesting. We'll see how easy or hard it is to probe this USB 3.0 with 8 gigahertz oscilloscope and very, very limited bandwidth 2.5 gigahertz probe. We have one 4 gigahertz probe available to us, and few 2.5 gigahertz probes are also available. Most likely we will be able to get away with decoding USB 3.0 with 1.5 gigahertz probe. We'll try to find out if we can make sense out of data. So let's get started. This is our setup. We're going to use Raspberry Pi, and right now I have removed the insulation from the USB cable, and there are 4 probes connected, 2 of my MDO 3000 because my MDO 3000 also can decode, and 2 of the probes belong to my MSO 804A. And right now it's connected to a keyboard, and keyboard is generally very, very low speed devices, so they use only USB LS, and that is perfect for in our scenario. We will try to find out when we do a key press if the data get detected onto the screen. So let's get started. We'll start with my MDO 3000, and we will do the same operation on my MSO 804A as well. So now I have overlaid the web view of my MDO 3000 so that you can better contrast. And you see there's a USB packet being decoded. And let's zoom in. The USB plus is connected to channel 1 and USB minus is connected to channel 2. It is a periodic sync packet, and you see that the host, in this case of Raspberry Pi, repetitively asks for data from the keyboard. When the keyboard does not have any data, the keyboard sends back NAC. This was packet is on the USB LS. As this is keyboard, this is USB LS. On this USB LS is supposed to get repeated around 8 milliseconds a time, and we will see if it's getting repeated 8 milliseconds a time. So let's find out another packet. There it is there. So let's measure using cursors, and we see this is 7.99 milliseconds. This is not a coincidence. The USB bus specification says that these kind of periodic updates are supposed to be happening every 8 milliseconds. Let's zoom in. Now we will try to set up a different trigger. We will do data packet trigger on any data packet. Okay, so zoom out. Let me press the key. I'll press a key, and now you see there's a data frame available on your screen. Now I'll zoom in. These blue bytes you see 100000, these are the key presses, and if I started to press buttons, you will see this data will change, and of course this CRC16 will also change, and I will let it run so that you can see it better. So now I'm pressing A. You see this data changes a bit, and CRC also changes with it. And if I press a different button, this third byte changes from 16 to 0. And if I press multiple buttons, multiple bytes will change, because this keyboard supports pressing of multiple bytes. And I think how many keys it supports, maybe 6 or 7. So this is 1 key press, 2 key press, 3, 4, 5, 7, and 8. So my keyboard has 7 key press maximum allowed. After 8, when I press 8 keys, you see all the data changes to 111111. which is denoting error condition. We are able to very easily decode and display USB on the oscilloscope. It's very easy to find and very easy to decode, at least USB LS. Now we'll go to my MSO S804 and we will see the same stuff there as well. So you see I have already set up the USB bus here as well, and you are looking at the decoded packet which is getting repeated. You're looking at the decoded sync packet which is getting repeated every 8 milliseconds. So maybe I'll let it freely. Let's zoom out and see if this is really getting repeated every 8 milliseconds. Yeah, so you can see per division is 2 milliseconds, and after exactly 4 divisions we see the repetitive package on channel 1 and channel 2 both. USB is a differential bus with NRZ encoding, and this is very well displayed there. See, I have already set up the trigger and I'll show you my bus setup. This is set for USB 2.0 low speed. What is special here, you're supposed to set this appropriate trigger level and protocol decode thresholds. This is supposed to be, depending on your bus, it should be appropriate level, otherwise your MSO 804 will not decode anything. Let's set up a trigger on data. We'll set up a trigger on data and any data for that matter, and let's see if it can decode anything. I'll again press a button and you see this data 0 came. Maybe I'll select it so that you can see what's the content. Okay, this is the data 1, and you see the data 1's packet content changes. Same third byte is changing. If I press multiple buttons, multiple byte changes. So this is our USB low speed detection and USB low speed decodation with MSO S804A. Is very easy. You set up a bus and just let the channels to be selected and it will decode you whatever the data you have. Now we will connect a USB low speed device. I'll try to connect my USB serial converter and we will see if the USB serial converter's data is getting detected or not. As a test platform, I have connected this development board from Texas Instrument to the USB device, and both of the oscilloscopes are still probing, and this device is detected as a USB FS rather than USB LS device the way keyboard was connected. Now we should be able to do some FS packet decoding, and you see I have also connected this UART in the loopback mode. These two RX pins I have connected, RX and TX pin, so whatever the Raspberry Pi sends to the USB chip should come back later. So we'll probe the UART as well. So I'll show you how in the relation of the UART signal being transmitted on the bus, what do you see on the USB side. We will do same experiment. First with MDO 3000, we will take the third channel of the oscilloscope. So I have taken third channel of the oscilloscope and I'll connect it to the UART. It is connected now, and now we should be able to see that UART packet is being received on the channel number 3 while USB is on channel number 1 and channel number 2. We will do same thing with the Keysight as well. We will probe the UART and probe the USB, and we will try to see the relation between the USB and UART package. So let's get started. So now we are looking at the oscilloscope one more time, and you see the packets are coming. I'll show you what I have changed. Zoom out, and the USB bus is changed from low speed to full speed. Everything else is remained same, and you see a lot of activity. There's a lot of activity going there. And because I have changed the trigger to sync, let's change it to maybe data packet or something like that. So there are data packets coming. Let's do maybe single capture. Now there is nothing coming. Okay, normal mode. I'll send some UART packets and we'll see if the packets get first of all detected on the USB and then second detected on the UART as well. You see, I'm sending a character. Character is just B, ASCII B, and you see that 62. Let me send a A. It should be 61. Yeah, now it's 61. B is 62. You see that? I'll maybe place the cursor, then you will see it better. Let's bring the cursor back onto the screen. Linked off. Bring cursor onto the screen. So you see where my A cursor is, this 62, this is the data content. And if I transmit A from my keyboard, you see it's 61. If I transmit B, it is 62. And we want to look at the third channel of the oscilloscope as well. Let me turn it on. It was already on. Let's see if it get detected somewhere on the UART. There's going to be a lot of latency there, but we should be able to definitely see it. You see the character. Maybe you don't see it. Let me turn on the bus. Cursors can also be moved to someplace else because I see it. You see there is an activity going on channel number 3. Channel number 3 needs ground. You see when I transmit the character, our trigger point is relatively stable, and right after the trigger point comes some characters, and that's what we are interested in. So let's zoom in. Yeah, there is a character. I'll set up second bus now. Not just the USB, we will be able to decode the UART as well. B2 is UART, define input, channel number 3, 115200. Parity bits, none, and this and everything else. Now I'll send something. Let's do a single capture so that we can see the packet. Yeah, so we see the UART bus as well. Its content is DF. I think it's not getting properly detected, but we will find out. Bus display need to change to ASCII. We'll do one more time single capture. Transmit A. No, it's not getting properly detected. I think it has to do with the threshold, define inputs, polarity is inverted. Yeah. Now I have transmitted A, and you see on A on the screen. Let's do one more single, and now I will transmit A one more time. You see A. Now I will transmit B. You see B. Transmit C. You see C. Transmit D. You see D. So it's as easy as that. It works really wonderful. Now I'll do single capture of a large message. Let's see if it does. So this appears to be a decent sized message. Let's find out what the UART transmitted. We need to do one more time single capture. Yeah. So it says welcome to, it will say welcome to Circuit Valley. I'll do one more time single capture. Let's zoom in now. So it's welcome to Circuit Valley and stuff like that. So let's look at the USB bus as well. I'll zoom in further and we'll see the packet content. So this packet has 3 bytes, 57656C, and let's change the bus display to maybe ASCII. Okay, so it says WEL, welcome. Okay, so of course it's exactly what we received on USB. This is exactly what get transmitted back. So because we are in loop back, same data should also go back. So we'll zoom out. Okay, and I'll keep the packet this time short, and now we will look at the event table of the P1. We have transmitted A, event table. Okay, data 0, 41. This is the 41 hex. So 41 hex represent A, which got received over the USB. Let's go down and we'll try to find out if 41A also get transmitted back. No, we do not see it. So we'll do a little bit larger capture this time, because you must understand, once the packet came in over the USB with content A got transmitted over UART, and same thing will be received, and this should be transmitted back because the loop back connection over UART, same thing should be sent back over the USB. I'll try to find out that packet as well. Okay, so USB is correct. We'll first of all try to acquire a lot more memory, 10 meg. We'll zoom out. I'll keep watch on my sampling rate. So now we capture the same packet one more time. Let's see if both will get detected. Bus is not yet computed. It takes some time before it computes all the buses. So now we have it. Now let's go to the USB's event table. Okay, so this is the trigger point. This is the first data which get transmitted in. Okay, let's go down, down, down. If we see any message going back, there must be going back message somewhere. So we have reached the end of the frame after how much? After around 2 milliseconds. Let's zoom out a little bit further. We'll do one more single capture. One more transmit A. Event table, same stuff. At 0 point we will see the data with 41 is there, and we need to find out the data going back. This oscilloscope does not have segmented memory, that's why we cannot capture one after another. What I will do, I will increase the memory depth to 10 meg. Okay, now I will zoom out as further as I can. I'll do single, and now I will do UART. So where the A is, our UART get detected. It's not decoded yet. So where the trigger number A, the cursor number A is, you see there's a tiny little blip in the channel number 3. That's my UART. And here, somewhere in this whole area, there must be a USB packet going back. I'll try to manually find out. Okay, so let's see if, first of all, we detect data coming in. The must be at 0. So time must be almost 0. 900 microseconds. That is my data A, ASCII A 41 hex. Okay, let's find out if we see the same thing going back somewhere. The UART stuff is not that fast, so it may be coming viel später. I still do not see it. No, I still don't see it. Even after 12 milliseconds, this thing is not visible on the screen for some reason. Maybe it's coming way later than 12 milliseconds or 15 milliseconds. What was that? Start a frame. What was that? Start a frame. So no. Start a frame. No, it's not on the screen. If you want, maybe I'll zoom out a little bit further. One more time, and we will do one more single capture. It will take some time before bus is decoded and computed. So let's look at the event display again for the USB. We are exactly on the bottom, so we'll first of all look from the bottom actually. 15 milliseconds, 16 milliseconds, SOF. That was also SOF. No, I do not see it anywhere at all. So for some reason we just cannot see. I don't know how much time does it have between two data packets. If you want, you can save the file somewhere and try to analyze the data on a computer. But we can find out the same stuff maybe a little bit easier on our MSO, on our MSO 804. I'll now go to MSO 804 and we will try to do same exercise one more time. So we verified with this oscilloscope, when data appears on the USB bus, it gets detected on the USB. It gets also transmitted on the UART, and somewhere here it must be getting back. We do not see it because we cannot able to capture it or missed it. But that's okay. We can try the same exercise on MSOS 804A. It has a lot more memory, way better display. Let's find out. Now we are at MSOS 804A. On your screen you can see there are 3 channels being activated: channel 1, channel 2, channel 3. Channel 1 and channel 3, they are connected to USB, and USB is currently configured as shown in MDA 3000 and a USB full speed, and it's connected to my TI dev board. And I'm also probing on channel number 2 the UART signal. Maybe I'll show you. Bring it in the front, and this is the UART signal. Right now our trigger and decode is set for USB and any data packet. So trigger somewhere here where it finds the trigger right in the middle, and you see the UART packet being transmitted. So our goal is to find out the packet itself. You see this data 0 is D. Let me transmit the A as well. So we'll do a single trigger, transmit A, and you see the data packet 0 is being received A, and trigger is in the middle. If you want, we can zoom in and look at the packet itself. Data packet 0, trigger point somewhere there, data packet 0, acknowledgement, and stuff like that. So this is perfectly being received, absolutely correct. Our concern, as you see, our concern was that this UART packet is being looped back. So we should see somewhere down the line on the bus that the same data packet 0 or data packet 1 with payload A should get back. Okay, and if you want, maybe we can first capture a long packet. I'll do a text transmission and you'll see that it's a little bit longer, and same thing we'll see there. Single capture, and you see this WE got captured, LCO got captured, welcome, X data ME got captured, 2 get transmitted twice, you see, 2. So they're being knack, and this is also one really good thing. You see, me got acknowledged. USB tried to transmit 2 one more time, did not get acknowledged. Knack, and finally ACK. Welcome to. So knack. It'll be welcome to Circuit Valley and stuff like that. This is the text I pasted. But it doesn't matter. We will try to move in. Okay. So now we will do one more single trigger. I'll transmit A one more time so that we can look for it. Same stuff. Our trigger point is there, and we need to look for or search for the incoming packet. So let's zoom out a bit. I'll zoom out pretty farther down. As I told you, this oscilloscope is quite deep memory, so I'll set up the memory. This is automatic. We'll take the memory to manual. Maybe we'll set both of them to manual. The memory we will take around 134, and 2.5 gigasample per second is enough. We'll do a single trigger, and I'll transmit same A, and it did trigger, and now it's acquiring or maybe processing for the display. So now this oscilloscope has a really decent feature, and it has a segmented memory. I think all the good Keysight oscilloscope have segmented memory. So we'll set up a segmented memory now. Segmented, we need maybe like 4 segments are enough. Can we go down? We can go to 2, maybe 4 segments are enough, yeah. So we'll let it to everything else remain same. Let's go down in this view, and let's see if we can also look at the segment itself. Okay, so we will do a single capture. I will press the same button A, and I have pressed it. Okay, so we got some segments, and now our oscilloscope's advanced segmented memory shows you how far that packet was. So you see, we captured 4 segments. One was at 0 second, second was at 80 milliseconds. So this is where Raspberry Pi sends the packets to the USB board, and this is where this little board receives the packet back over the UART and try to transmit it over USB back to the Raspberry Pi. Same thing, 4.32 second, I transmitted twice because we tried to capture 4 segments. So it happens after many seconds. I press the button one more time, and exactly after around, you can see this is almost like 80 milliseconds, exactly 80 milliseconds. So if you want, we can do it one more time. Let's do it one more time. We'll do 2 segments only. Okay, so I'll let it run one more time. I press the button. So it did capture 2 segments, one at 0, one at 80 millisecond. So this segment 39 data 0A loop backed 48 data 0, data 1 is set to 1. So it is as easy as that to capture segmented memory, and it was very easy to handle segmented memory, and that's the advantage of having segmented memory. You can wait for many events even though they are far apart from one another, and you can still capture quite a decent amount of waveform. So this is, we have proven that we can decode very easily USB FS, and now the challenging part is try to deal with USB HS. I'm going to try to find out how can I deal with USB HS. So I'll see how it goes there. So the setup remains same. I have removed my MDO 3000 because it cannot decode USB HS, but I'm going to try to decode USB HS with this guy. But now we need to really take care of the signal and everything else. We cannot just leave it there, and we will try to find out if, first of all, disable the segmented memory, and we don't need channel number 2 right now. So I have connected a FTDI cable in the loopback mode, and this cable is C232 HD, and let's set up the trigger first to edge trigger so that we can look at the signal before we try to decode the USB. Let it run. So you now see the signal quality is signal level is very low. It was expected. So we'll increase the time base. So increase the voltage base. Set the trigger point a little bit lower. Trigger is right now set to channel number 3. Let's set it to 1. Now edge trigger should be low a little bit. Let's zoom in. You see, this is the USB HS transmission. This is fast stuff. If you want, we can analyze and set a marker there. Okay, so fastest time is something like this. Starts from there and goes up to here. So you see this around 480 megahertz. Of course, this is 480 megabit per second. So this is what you see as a delta on the pulse, and it is really USB HS. And we will remove the markers now. Okay, let it run. Signal quality is good enough. We can decode with it. There's a lot of overshoot, undershoot, and this kind of shit is happening. But I think we can deal with it. Which channel it is happening? It's happening on channel 1. This is the problem with this kind of high-speed probes, and we are still probing with that broken cable or that unisolated cable. You generally do not do that with a 400 or a 480 megabit signal, but we can still try to decode it. Maybe we'll increase the voltage base so that it looks better. I'll get this lower. No, it will not work. We need to have it at it is 100 MB. This is 100 MB. Both set to 100 MB, and we can now decrease them. So now signal looks like something we can deal with. So let's set up a decode. USB 2.0, and it's a USB high-speed data. Channel 1. This is the first problem which we face. You see in the protocol decode window, it's only accept a differential source. We don't have any differential source. So we'll go to the prop menu and make a differential source out of them. Okay. And differential between channel 1 and channel 3. Yeah. And that's it. So we'll do one more single capture. And look at the signal. Signal got better. Oda. We can disable the channel 3 display. And display. Setup. I need only one grid. So this channel, even though it looks like a channel 1 capture, you see it's very clean now. It has removed many of these overshoot, undershoot. That is the advantage of having a fancy oscilloscope. And I'll show you one more time the trick. Differential channel 1 and channel 3. Okay. So now we can set up decode. Channel 1 and channel 3. That's it. Can't perform decode, not enough edges. Maybe it didn't find the edges because it didn't find the appropriate threshold level. Threshold level need to be set manually maybe. Let's see how far up it is. Should be maybe like 200 MB. Maybe 20 MB. Okay, so we'll do one more single capture. Can't perform decode, didn't find sync. Can't perform decode, didn't find sync. Let's do one more time. It still didn't find sync. So now I believe this cable quality or this cable will not work as easily as it looks. I will flip the board and I will try to probe directly on the bus rather than I'll try to probe directly on the connector and not on the bus itself. I'll show you in a second. So I have flipped the board and you see this C232HD high-speed USB cable is connected right there, and you see these two test points which are directly on the USB connector. These are the test points we are going to probe. They are USB HS test point. They are primarily used for Raspberry Pi production, but we can also use them for our own testing. We'll try to somehow hold these probes something like this right there with the appropriate ground, and you see this probe has also a very appropriate ground connection, and we will try to measure right there with the appropriate ground, and we should be able to see a good signal with that. So let's do it and I'll show you the setup then. So this is our board flipped and I'll show you this. I will hold it like this. I do not have any probe holder, so I have to hold it. My ground is spring loaded, and this I have self-made grounding post. I will ground it and right there we'll probe it like this. I will hold it and you will see an overlay of the screen. When I trigger it, how does it look? I have triggered it. So signal quality, does it look better? It's way better. Okay, so sometimes you have to do this kind of weird finicky things. I do not know if it is not detecting sync because positive and negatives are exchanged. Generally you can go through towns and try to find out if it is umgetauscht or not, or you can just exchange it yourself, and then if it detects other way around, then we are happy with it. So after holding probe, signal looks very clean, and you can see it's pretty much understandable. And now I'll set up the decode. This stuff is really important. It's trigger level, it is around 60-70 MB, that's okay. We will change the trigger type, and this thing you need to change the threshold to 0 and maybe change it to 50 MB hysteresis. That should do. Okay, so now we see we are decoding the bus, and if I zoom out, you see many of this SOF packets are coming, and this is the USB HS bus, and now we will try to transmit something there, and we will see if it gets also detected with it. So now I'm holding it, and you see there's some kind of STX data coming in. I do not know what it is. It doesn't matter to us. We will transmit our data, or maybe we'll set up a better trigger. Okay, and we'll see payload, and you remember it's supposed to be 41 hexadecimal for capital A. Now we will transmit this 41 hexadecimal for capital A, and we'll see if we get triggered. At this moment we are trying to do it. I am sending some stuff, but I do not see any trigger happening. This may be for various reasons. It may be not data 0, it may be data 1. So let's change the trigger and try our luck there. 41. Enter. So let's send 41 one more time. I see it being looped back, but doesn't work. Trigger setup, data 2, 41, enter. I still do not see. I see the data being transmitted, but I still do not see it being received or transmitted. No trigger at all. I assume that this transmission of data in this FTDI chip is a little bit different than the Texas Instrument chip. That's because the data on the USB bus is going to be transmitted through data packets, and for some reason we cannot trigger to these data packets. So now we are capturing on data. Now we will stop it, and now we will try to capture a few segments. segment. I think 512 segments will be enough. I will continuously transmit symbol A, capital A, hexagonal symbol 41, and we will try to let it run at the same time, and we should see some of the packets, data packets may be carrying our data. We want to see the format of it and stuff like that. So I have let it run, and it capturing segments. You see is 240, 290, 300. Now it should have soon 500 segments. Yeah, now we have 500 segments. Okay, so you see, with the help of segmented memory, we are able to find our data. I believe this A, which you see in this packet, 026041, this is our A. And as I'm pressing on the keyboard, on 0th number second, it got detected. After 16 milliseconds, there is no A in the packet. After 32 milliseconds, again not there, again there. So I'm repeatedly sending A, and alternate packets have my content. I'm pretty sure that FTD sends these 0260. I do not know what does 0260 means, but it definitely sends 0260 before my data. That's what we are going to trigger on. So I'll set up a trigger. Let's see which data it is. It is data 1, data 0, data 1, 0, 1, 0. It's on data 1. So I'll set up a trigger on data 1. Data 1. Okay. So remember 026041. So 0260 is the standard thing which is coming always. And now let's see if we can, I don't need a segmented memory now, I'll do real time. 512 samples are enough. I'll let it run in the triggered mode, and I'll hold the probe, and we will see that if my data get detected, I will transmit A first. This is A again, data 1, 026046. Now you should be able to see different characters. Now we're waiting. This is A, this is B, okay, this is C, D, or maybe D is D, E, F, G. So this is the format of FTTI FT232, and it always sends this 0260 beforehand, and then the data comes up. So I think that's it for this video. This video is already quite long. Till now we have covered 11 protocols, and the next video is going to be about MIPI and PCI, and we'll see how we can decode these two advanced protocols which are not normally known on the internet. I have already published many videos using MIPI, and we'll try to decode this time. We'll see how the camera, sensor and display interact with one another and stuff like that. So keep watching. You can visit my website www.circuitvalley.com.